Hello everyone, welcome to this presentation on the Foucault pendulum properties of spherical oscillators. We'll start by presenting the Foucault pendulum before moving on to spherical oscillators and the work that has been done. The Foucault pendulum is a famous physics experiment which is a direct demonstration of the Earth's rotation. It consists in a pendulum which is launched from the center in a straight line. This defines a plane of oscillation. Following the principle of inertia, the plane of oscillation will remain fixed in respect to an inertial frame. However, for an observer on Earth, this plane will rotate. When looking more closely, the Foucault pendulum is nothing else than a 2-degree of freedom oscillator, and its principle can be extended to other oscillators, which is the main idea of this project. In this project, we extend the Foucault pendulum principle to what we define as spherical oscillators. These oscillators consist in a spherical mass who can rotate around its center. It has 2 degrees of freedom, as the first degree of freedom is choosing in which direction to tilt the sphere, and the second is how far we tilt the sphere. There's naturally a restoring torque which tries to put the sphere back to its primary position. As the spherical oscillators' kinematics, dynamics, and Lagrangian are different to the pendulum, the Foucault behavior of the spherical oscillator will be different. The plane of oscillation will neither remain fixed in respect to the inertial frame, neither will it follow the rotating frame. It will have a precession at exactly half the rate of the rotating frame. This intriguing result provides the goal of the project, which is to validate experimentally that when the spherical oscillator is placed in a vertical rotating frame and undergoes linear oscillations, the plane of oscillation precesses at half the rate of the rotating frame. The oscillator used in the demonstrator is based on the previous design. This involves flexures which provide both the desired kinematics as well as the restoring torque. These flexures consist in 3 equatorial beams which lie in the horizontal plane and 1 polar beam underneath. Here's the implementation of the demonstrator with a CAD view on the left and construction on the right. One can notice the motorized rotation stage beneath the oscillator on the CAD view. It's this turntable that induces the Foucault effect, as the Foucault effect from Earth's rotation is small and difficult to detect. Here's an example of the results in which the left diagram shows the trajectory of the sphere when released while placed on the rotating table. As the plane of oscillation should precess at half the rate of the table, plotting the shift of the plane of oscillations in respect to the shift of the table should have a linear behavior with a slope of 1/2. On the right, there is the corresponding plot with a slope of 0.45. This experiment was performed with different table speeds. You can see that the slopes are close to the expected value of 0.5, with the exception of the slowest table speed. This last result differs as its smaller Foucault effect is dominated by parasitic asymmetries in the construction. We have now presented the demonstrator and results that validate the Foucault behavior of spherical oscillators. This work presents the possibility of showing the Foucault effect with oscillators other than the pendulum, which requires a tall ceiling. Thank you very much.